Let's go ahead and get started for today. So now that our exam is over, we will be starting on the next overarching topic for the semester. And I figure a good one to do is fluids. Fluids is an interesting subject. It's very important in a wide range of subject areas. Of course, the main one would usually think of for fluids would be something like engineering, civil engineering, and things like this. Understanding fluid flow and the like is important for city construction and all of that, even down to a single home construction, or if you're planting a garden and you want to know how much hose you can use if you're using like a soaker hose to water the garden, and you want to know how long can the hose be and still be able to get enough water pressure at the end to be able to water your plants and all sorts of stuff. But it goes further than that, of course. We could talk about medicine, medical physics, or physical therapy, or all sorts of different topics in medicine, where, of course, you want to know about blood flow through the veins and the arteries and capillaries and all sorts. But one thing that needs to be understood, and is kind of shown that it needs to be understood based on what I've already said, is the fact that fluids, when we use the word fluid, generally speaking, in our everyday world, we're talking about liquids. But in terms of physics and in science, fluid actually is not just liquids, but also gases as well. And so, for instance, one of my areas of research when I was getting my doctorate dealt with what's called poroacoustic fluid flow. And what it means is you have some kind of a medium, maybe it's sand, a sponge, some medium that has a bunch of pores in it, little bitty holes. And then that medium is filled with a fluid. So that could be water and sand, like at the bottom of a lake or Gulf of Mexico or something. Or it could be the water that is in a sponge, or if you're making coffee, the coffee grounds act as a medium with pores because, there's areas where the fluid can flow through the medium. And then you have a fluid permeating this medium. So it could be the water, it could be air, it could be blood going, or, in the liver or the kidneys, all sorts of things. And my area of research dealt with how does a sound wave, which passes through this system, react. And one of the reasons you may want to do this is if you're, for instance, you want to see if there's oil under the ground, because obviously that's important to the country, being able to have our own oil, especially in these times. But you don't want to have to drill. Maybe it's difficult to drill, or you don't want to mess up the environment just to see if there's oil if you don't know yet. There may be different reasons. And so one thing you could do is send a sound wave down, let it pass through the ground a certain distance. The sound will reflect. You'll have little machines, detectors detecting this reflection of the sound wave. And then you compare the reflection to the original source. And then if you know enough about poroacoustics, then you can actually determine what must be under the ground, what the sound wave reflected off of, and tell what's there. So for instance, you could send a sound wave down to the bed of a lake and get the reflection back and be able to see, is there oil underneath the ground level, or is it just water, or is it different types of sandy materials or whatever. And so there's lots and lots of areas where this is important, but It's not just liquids, it's also gases. So be sure that whenever you're listening to someone or you're talking appropriately in a scientific setting, that you understand when a person's talking about how fluid will flow, they could also be talking about the air in the atmosphere. How does the air flow around based on the pressures and things like this? So first thing to know, fluids, liquids, or gases. Now, this particular course, as I said at the beginning of the semester, generally we're going to be looking over these topics that we're going to be getting later in general physics and down the line at a more basic level. So rather than going super detailed into everything, we're just going to kind of touch on the most important aspects. And that way, when we get to these subjects in general physics courses, you will be used to it. You'll kind of already have a nice foundational understanding, and you can start to get into the details and the more complicated questions, and it won't be such a big deal. It won't be the first time you've ever heard any of this. And that's true for this topic we're going to be doing here. Obviously, I can't get into everything about fluids, but we're going to cover some of the most important aspects. And the first one we're going to get into is going to be Bernoulli. Bernoulli's principle. Is a very, very important topic in fluids and fluid flow. And to do this, we're going to have to understand a couple of terms that may not have come up in the past yet. So we'll define them, of course. The first thing we need to define is the fact that in fluids, what we see, or what has been developed thus far, is one characteristic, which is usually very important in physics, is not going to be the characteristic we use here, and that is mass. So generally speaking, mass is extremely important. Obviously, with mechanics, F equals ma, force is mass times acceleration. That's the big physics equation, Newton's second law. And you need to know the mass of an object to understand how a force will affect that mass. How fast will the object move? How easy is it to get it moving or to change its motion? It goes into gravity. How will a planet react to the sun? How is its orbit? Depending on how massive this planet is. Is it very, very small planet like a satellite, or is it very large like Jupiter? It goes into all sorts of different areas. However, with fluids, the mass itself is not necessarily what's important. And one way to see this is to think about whether objects will sink or whether they will float. And so you could say, well, I would imagine, just intuitively speaking, that if you have a body of water, let's say a lake, you're standing at the edge of the lake and you have some different items and you want to know if that item will sink or float by throwing it in. You say, well, probably what's important is how heavy the object is. The heavier the object, the more likely it is to sink. That's just intuitively, it seems reasonable. You throw a big heavy rock into the lake, it's going to sink, but you put, a piece of paper and it's just going to float on the top. So in our minds, we already have this kind of thought that maybe the mass is what tells you whether something will sink or float. And so you do an experiment. An experiment is you have an ice cube, very small piece of ice. You have a regular size rock. And then you have a big, huge metal boat. Okay, so the ice is the lightest thing. The rock is medium weight, half a pound or something. And then a boat is a few hundred pounds. And so you start putting things into the lake. The ice, you put it on into the lake, and sure enough, this ice floats. Perfect. Ice is very, very light, has a very low mass, so it floats. Then you get the rock, which is heavier. You throw the rock into the lake and it sinks. So that's perfect. The rock is heavier than the ice floats, the rock sinks. So obviously the heavier object sinks, lighter objects will float. But then you get to the boat and the boat floats. And this is weird because the boat is certainly heavier than the rock. So one would imagine that if the rock would sink, then so would a boat. But we see that it doesn't. And so this immediately tells us that it's not exactly the mass or the weight, if you want to think about it as weight, but the mass of the object, which tells you whether an object will sink or float. Certainly it has something to do with it, because you rarely see something light sink. Light things always seem to float. And most of the time, heavier objects sink. So there's some relationship, but it's not just purely the mass. And in fact, what is important is a different characteristic, which is related to the mass. And this is called the density. The density of an object is the thing which tells us whether something will sink or float. So about the density, what is its variable? The variable is called rho, R-H-O. This is the Greek letter rho. We ran out of our normal letters in our alphabet, so we had to start going to the Greeks. And so we picked this one. And now I have a slight quirk, which I'm about to explain, which is a personal quirk of mine. But first of all, when I write or I draw, or however you want to put it, when I write the letter rho, I write it like this. Okay, it's like a P with a curly tail going down to the left. Okay, this is not how the letter rho is actually written. When you see the letter rho written by almost everybody in the world, they write it like this. Okay, it's similar. It's a curly P, but the tail curls to the right, down and to the right instead. I choose not to do it that way. First of all, because I'm not Greek, so I'm not writing a bunch of Greek letters to people. And when it comes to actually official documents, if I'm getting an article published or something, obviously I use normal word processor typeset, which will do it correctly for me. So it's just in my own notes, I draw rho kind of backwards. The tail goes backwards. And the reason is because when I write rho, especially if I'm writing it quickly, I had to do this fairly slowly, it looks like the letter E to me. And so it could get very, very confusing. So I draw the letter rho with the tail going back the other way because I know it's not P since the tail is curly. And it doesn't look like the letter E, it looks like its own letter. And so that's why I'd write it like this. So just know that that's true. You could write it any way you want. The correct way, which is the one that looks like an E, sort of, or the way I do it. But just know that when you look at mine, if you're ever going to look in a textbook or you watch YouTube video of some other professor going through, he's going to draw the letter differently, and his is, or hers is correct, not mine. So just know that from the top. But anyway, that's the variable rho for density. And what is it? Well, density is defined as the mass of an object divided by the volume of the object. So M is mass and V is volume. And so what this says is, yes, the mass is important when we discuss fluids. Obviously, it's important. However, it's also how that mass is kind of spread out. If you have an object of a certain mass, let's say it's 10 kilograms, and all 10 kilograms is in a very small little object, so like a rock, or you have a 10 kilogram object which is spread out in a very big object. So these are both 10 kilograms, but obviously this boat-shaped thing over here is very large, whereas the rock is very small. Well, they have different densities. The density of the rock would be a lot larger than the density of the boat, because for the same amount of mass, you have a much bigger object. So that mass is kind of spread out over a large volume rather than being concentrated in a small volume. So that's what density is. Now, also the units, if you want the units of density, well, just look at the equation. Density is mass over volume, so it's kilograms for mass and meters cubed for the volume. So that's the units of density, kilograms per meters cubed. There's no fancy replacement unit like with newtons, kilograms meters per second squared, and they take all of that and they make it one letter, the letter N for Newton. They don't do that with density. Density is just density, kilograms per cubic meter. Now, one way to ensure that you understand there's a big difference here between, or why it's important to understand density versus just the force or just the mass itself, is to think about something related, which is like a bed of nails. So if I said, here is a wooden plank, and I stick one nail on it right there, and then over here, I've got a wooden plank, and here I have 1,000 nails across it. And I ask you, you have to lay down on one of these. Which one would you rather lay down on? Well, certainly, I would much rather lay down on the bed of nails rather than the single nail. And the reason, of course, is with the single nail, when you lay down on it, all of your weight is pushed down on this one nail. And so surely that nail is going to puncture you. It's going to go right through you. However, with the bed of nails, your same weight is pushing down. It's just that now your weight is spread out over a whole bunch of nails. And so each nail doesn't feel the full weight. Each nail only feels a piece of your weight. And so maybe if you have enough nails spread out, then the amount of weight which is on each nail is not enough for the nails to actually puncture you. And in fact, if you do this at the extreme, well, let's just, a wooden board. If you lay on a wooden board, you could think of it as, a trillion wooden splinters that you're laying on. It's just that there's so many, it feels like a complete solid surface. You don't feel each individual atom. You don't feel each individual piece of wood, let's say. And so this is like the concept of density. If you have all of your weight, but it's in a very small location, it's different than if you have your weight and it's spread over a very large location. That's why density is such an important concept here. And for our purposes, the thing to understand about density is that objects float when the density of the object is less than the density of the fluid. And of course, vice versa is true. Objects will sink if the density of the object is greater than the density of the fluid. And so if we look back at our three examples from the top, we have a piece of ice, a rock, and a boat. The reason the ice floats while the rock sinks is not necessarily because the rock is heavier. That's part of it. But not only is it heavier, its density is bigger as well. And that would also explain why ice would float to begin with. If you think about it, ice is just water. All you did was make the water cold. But if you put water into water, the water can sink or it can float. It moves all over the place. It's completely, let's say, buoyant. It just passes through the water. And of course, you know, some of it will go down to the bottom just naturally as you pour. But if you put a piece of ice in there, it's still the water, all of a sudden it floats. Well, the reason is because when you freeze the water to create ice, it doesn't just create ice, it doesn't just become solid, it also changes its density. It actually expands, it gets bigger. And so a piece of ice of a certain mass is bigger than water of that mass. It's the same amount of mass, but the piece of ice, since it's expanded when it froze, actually has a lower density. More volume means lower density. And that's why ice would float. And then the boat over there, yeah, it's a lot heavier than the rock, but a boat is also a lot bigger too. It has more volume. And so depending on what boat you use, if it's a good boat, then its density is actually less than the density of water. And so that's just something to understand. If you want to know whether something will float or sink in a liquid or a gas, of course, the same is true in a gas, which is gases have extremely low densities. But in a fluid in general, an object will sink if its density is greater than the density of the fluid you're putting it in. And that's all you need to know. You don't need to know anything else about anything. You know the density of the fluid and the density of the object, you'll know if it'll sink or not. And just for your information, the density of water is 1,000 kilograms per cubic meter. Okay, so that's a number we're going to use a lot when we do example problems. Density of water is 1,000. And then, of course, you have a whole bunch of other types of fluid. Honey, of course, would have a bigger density. Metal is a bigger density. Foam is a lower density. Gases are a lower density. So that's the first big thing we need to know, density. Next thing we need to know is the concept of pressure. So pressure is also going to be an important concept. And what this is related to, like density was related to the mass of an object, for pressure, pressure is kind of like a force. Okay. So when we talk about, let's say you go underwater, or yeah, as you dive down into water, we know that it's dangerous to go too deep. So scuba divers and the like have to be very careful how deep they go. Why? Because as they go deeper and deeper, the water that's surrounding them, that they're in, starts to apply more and more pressure. And so first thing we need to know is what the heck is pressure? First of all, the variable is capital P. P for pressure, which is nice. Capital P makes sense. The equation is how much force is being applied to an object divided by the area over which this force is being applied. Okay, so it's not just how much force is there, but it's also the force applied over an area. And that again goes to this bed of nails concept. As I said, as you lay on this, one or the other bed of nails, the force that's involved is the force due to gravity, your weight. So in both cases, it's your weight being the force which is applied. The difference between the two examples is how that force is applied. Is it applied at a single location, a very small area? That's the single nail. Or is all of your weight being applied over a large area, which is what the bed of nails would be? And so for the same amount of force, it feels different to us. If you feel the one nail, it hurts. It punctures you. It goes through your body. But the bed of nails, the same amount of force, all of a sudden you don't even feel that it's nails. It just feels like you're laying on a solid piece of wood or something. So pressure is what's important here, not just the force. And of course, if we want to get to the units, F is force, A is area. The units of pressure, looking at the equation, is newtons for force and meters squared for area. Now, this does have a fancy unit, okay? You could think of it as newtons per meter squared, which is fine, or you could call it the Pascal, PA, Pascal. And just like with newtons, kilograms, meters per second squared, they got tired of writing that. They just call it the Newton, the capital N. Here, newtons per meter squared, they call that a Pascal. Okay, now this is the metric system. Of course, if you're going to be an engineer here in America, where we use the imperial units, you don't use pascals. You'd probably be using something like PSI, pounds per square inch. So if you ever go pump up your bicycle tire or car tires or things like that, generally speaking, the units, the gauge that you're looking at how much air you're putting into the tire is in PSI. And that's what it means. It's the pressure of the fluid inside of the tire. Pounds per square inch, this is newtons per square meter. It's the same type of concept, or you call it a Pascal. That's generally what we call Pascal. Now you will also see other units, okay? Another unit you may see is called the atmosphere, ATM. That's another unit. And all this is understanding the fact that we live on the Earth. The Earth has an atmosphere, and the atmosphere is a gas. It's a series, a combination of nitrogen, oxygen, all sorts of things. And gases are fluids. And so we're constantly in a fluid as we stand here on Earth. And so that fluid must apply a pressure to us. It's surrounding us. It's trying to push on us, trying to squeeze us. And the fact that we're born into it and we live our whole lives in it means we don't notice that it's there. What we notice is when we get into other fluids. So when we get into the water, the pressure increases because, of course, the water has a greater density and things. And as you go deeper and deeper into water, you get more and more pressure. All of a sudden, things start to crush. Even nice big metal submarines that are designed for it can only go so far before they're crushed by the pressure. So we're currently under pressure, just sitting here in our room. It's the pressure of the atmosphere. And the amount of pressure that the atmosphere applies, which I believe is, I risked doing this, but I think it's 1.018 times 10 to the 5th pascals, something like that. Don't quote me. Of course, you could Google it, but one atmosphere is actually a very, very large number. It's a huge number of pascals, tens of thousands. But because we lived with this pressure our whole lives, it never really changes. I mean, yes, as you go up a mountain, the pressure decreases, and but we don't notice it that much. We feel our ears pop or things like that when we go into an airplane, but that's really it. We don't know, we don't feel this pressure, but it's there. And so whatever this pressure is, this number that we're constantly at, that's called the atmosphere. And so then we could say, oh, when he got into the water and he went down 100 meters, he felt 3 atmospheres of pressure. What it means is 3 times this number of pascals. It's just the same as if you're a fighter pilot and you're doing some fancy maneuvers and people would say, oh, he felt 6 Gs. What they mean when they say 6 Gs, they're trying to tell you something you can feel. And it's like, well, you live in 1 G, So you feel 1 times worth of gravity's force acting on you. If you feel 2 G's, then the gravity you feel is like twice as much, or you feel twice as heavy. 4 G's, you feel 4 times as heavy as you normally do. The normal being 1 G of gravity. Well, here, same thing. We feel the atmospheric pressure, and when we go up in pressure, we say we feel 3 atmospheres. Okay, the Pascal is the correct unit, but sometimes, just as is true if you're in chemistry and you start using slightly other units because it's more useful, here, sometimes you'll see the atmosphere as another unit. So just look out for that. But for us, we're using pascals. So those are the 2 big new concepts we need, or new characteristics, variables. The density being rho, mass over volume, how dense an object is, and then the pressure. The pressure, which is kind of like the force, how much force is applied to an object, but it's not just the force, it's how is the force applied? Is it applied over a big area or a small area? All right, so first of all, are there any questions so far? All right, good. Yeah, nothing too complicated yet, just kind of introducing stuff. So now we can talk about the big equation, which I started at the beginning, which is Bernoulli. Bernoulli's equation. Now, this equation is kind of going to be similar to when we talked about conservation of energy in first semester physics. Conservation of energy told us, all right, every system has a certain amount of energy, and that energy can be split up into 2 different pieces. One is kinetic energy, which is the energy you have because you're moving, and the other is potential energy, which is all the other types of energy. So gravitational potential energy, electric potential energy, heat energy, all sorts of things, whatever. And what conservation of energy said was that if you add up all the different types of energy in the system at the beginning, then at the end of the system, it should still have that same total amount of energy. It's just that how the energy is split in the first part may be different than how it's split in the second, but the total energy is the same. Well, Bernoulli is going to do something very similar, but this time it's about pressure. The pressure in a fluid system. And a fluid system we're going to be dealing with is going to be like pipes, water flowing through pipes. Okay. And so this, I'll just write down Bernoulli's equation. It says the pressure in the fluid at one location. So this may be, you have a pipe system and there's a pump pushing the water through your pipes. Okay, so this pressure is like how much pressure is applied by a pump, let's say. Plus, now so that's like the kinetic energy. It's not kinetic energy, but you can think of it like that. Now we're going to have pieces that are like the potential energy. Other pieces which are still pressure, but they're pressure due to some reason. So the first one is the pressure due to how the fluid is moving. And it's 1/2 rho v squared, where, okay, rho is density, of course, and v is velocity. So it turns out that how fast a fluid moves changes the pressure felt by the fluid. Okay. And we'll discuss that in greater detail when we talk more about this. But for now, that's just another term. There's a term there that is the pressure, let's say due to a pump. Then how is the fluid moving? That tells you about its pressure as well. And then another term, which is how is the pressure changed because of how deep it is, or how high the pipe rises, or whatever. And that's rho times G times H. So of course here, rho is density, G of course is 9.8. the same acceleration due to gravity. H is the height. How high does the pipe rise, or how low does it go? So if we're talking about, let's say, a house, and you have water pipes that go in on the first floor, feeding your kitchen and your bathrooms and all of that, and then you want to get your pipe, the water go into the shower on the second floor, well, the pipe has to go up to the second floor. And the fact that you're trying to push the water up to the second floor from the first floor means there's a certain amount of pressure you have to apply to allow for that to happen. So how high or low the pipes move will have an effect. And so if you add all three of these terms together, that's kind of like the total pressure in the system at one location. So all of these have ones on them. Pressure 1, velocity 1, height 1. Equals all the same stuff, but in a second location. So P2 plus 1/2 rho V2 squared plus rho G H2. So you can see very similar to conservation of energy. If we think about what that looked like, it was kinetic initial plus potential initial is kinetic final plus potential final, right? You add up all the energies, you get the initial energy. Conservation of energy says initial energy is constant. Whatever it is here, it's going to be the same energy over there too. Well, Bernoulli, same thing. How much pressure do you have here? The total pressure is going to be constant no matter where you check in your system. You check at the beginning, it's something. You check at the end, it's the same thing, but maybe now the fluid is moving faster, and so the pressure changes. Or you went up, the pipe went up to the second floor, so the velocity will change or something. But the total pressure remains constant. And so this is Bernoulli's equation. This is the big guy we're going to be using to solve a bunch of our problems. Now, different problems will have different uses for this equation. In other words, maybe I have a pipe system where the pipe is always on the first floor. It doesn't go up, it doesn't go down, it just stays at the same height the whole time. Well, if that's the case, then rho GH1 is the same as rho GH2, so they would cancel, so you don't need them. And so if I were doing a problem like that, I just wouldn't have rho GH in the problem anymore. Just like with the conservation of energy, remember potential energy can be gravitational potential energy or spring potential energy. But if I don't have a spring in my problem, well, I don't write the spring potential energy. It's not there. I just ignore it. Same for this in Bernoulli's equation. If the pipe doesn't change height, I don't write the height part. I just have the other two pieces. Or if the fluid velocity doesn't change, I don't write that part because you don't need it. But the full equation has all three. Now, what does this say? Bernoulli's equation. Well, a few things are interesting. First of all, if we were to look at a problem, or what does a pipe system, a typical pipe system look like as an example, it would be something like this. You have a pipe, here it is, and you have your water flowing through it. And let's say the pipe is a certain size. Okay, and so it's got some radius. Okay, it's a nice cylindrical pipe, a normal water pipe, and it's so big, whatever its radius is. And it's going along, then it goes up to the second floor. So it raises up like this, and it just continues on. So the water's flowing. And then maybe the pipe constricts and becomes smaller. And then it gets to wherever it's going. Let's say the shower or something like that. And so over here, the pipe has a different radius, some R2. And maybe the velocity of the fluid is something over here, and maybe it's something else over here. And we know how much the pipe height changed, right? So maybe H1 over here and there's H2 over here. Something like that. That is what a typical Bernoulli problem will look like. There's a pipe system. We have information about the size of the pipe, about how fast the fluid is going, all that kind of stuff. And we may ask a question. Maybe we want to know, how does the pressure change from the first location to the second location? Or how high should I make the pipe go in order to make the pressure in the shower a certain amount? Different things like this. Those are the types of questions you could solve with Bernoulli's equation. Now, one thing to note is, why in the world do I care about the size of the pipe? Notice Bernoulli, it's got pressure, density. So that what kind of fluid is this? Water? Is this air? Is this honey? What's flowing through my pipe? That's the density. V is the velocity. How fast is the fluid flowing? H is how high the pipe goes. Notice there's nowhere in Bernoulli's equation I talked about the size of the pipe, the radius. Yet I put it in this little picture. Why did I put it there? And this, by the way, if your goal in life is to be a scientist of some sort, whether it's an engineer, being an applied scientist, a physicist, being theoretical or experimental, or you're going into some other field that's science related, this is something you have to do. First thing is, always be not a critic. What do they call it? When you don't believe things told to you. Always question, okay? Even question me. Don't assume I know what I'm talking about, although I do. I'm not lying to you. But as a scientist, a skeptic, that's the word. Always be a skeptic about everything. Because that's the whole point of science. It's to not believe what's told to you, but to prove it. Someone does an experiment and says, hey, I just figured out how gravity works. The acceleration due to gravity is 9.8. You say, huh, that's interesting. I better find out if this is true, because I'm not going to base all of my work on this person telling me the value's this. I don't know if they messed up in their experiment. I don't know if they're just making it up. You know, they have some reason to make up data. Maybe they're getting, funding from the government to do specific research, and they know that the government wants certain results and they don't want other results, and so you modify what you do. There's a lot of ugly stuff out there. And then even at a lower level, the point of skepticism is to try to find out what's new. We don't know everything. We know a lot. We figured out a lot as physicists and scientists in general, but we don't know everything. There's stuff we're not sure about. There's stuff we think we understand, but we know for sure we don't understand it exactly. We understand it at a level that's useful to us. For instance, quantum mechanics and gravity, or by gravity, I mean general relativity. Physicists know a whole lot about quantum mechanics, and they know a whole lot about general relativity. And they both seem to work very, very, very well. However, the moment we try to apply quantum mechanics and gravity together, everything breaks down. And so that leads us to know, or to understand, that there's something wrong in one of them, at least, if not both. Because this universe, obviously, all the laws play together perfectly well. A black hole knows how to work. We're just trying to figure out how it works. And when we try to figure it out and we use the theories we know, quote unquote, we know now, they break down. So obviously the universe is not exactly what we think it is right now. And that's the stuff we know for sure, much less the stuff we're just guessing about. So first thing as a scientist, always be skeptical, but also question things like I just did here. I gave you Bernoulli's equation. There it is in all its glory. And then I tell you a typical question looks like this. And I have these pieces of information in this question that have seemingly nothing to do with Bernoulli's equation. And so the first thing that should come to your mind is, I wonder why there's radius there. What does a radius matter? I look at the equation and it doesn't look like it. And I'll tell you why it matters. The reason is because here's a good way of thinking about it. Let's say you're back in your garden, go outside the backyard. Let's say you have a house and you're growing some tomatoes or something, and you're going to water your garden. So you have your hose, you turn it on. One thing almost everybody does, unless they have a fancy, head on the hose, is they'll put their thumb over the end of the hose. And what happens? Well, when you don't have your thumb over the end of the hose, the water just comes out as it comes out. But when you put your thumb over the end, all of a sudden the water shoots out a lot further. And so one question is, why in the world does that happen? What's going on? We know to do it, we see it, and I'm sure everybody's done it at some point in their life. Without understanding why in the world it works, it just does work. That's all you need to know. Well, of course, as a physicist, you need to know why in the world it works. And the reason is because the speed or the velocity of a fluid flowing through a pipe depends on the size of the pipe. So with the example of the thumb over the end of a hose, what's happening is the pipe is a certain size, the hose, and water's flowing through at a certain velocity. When you put your thumb over the end, what you've done is you've constricted the pipe. Now the pipe is a lot smaller for the fluid to try to flow through. And so in essence, what you've done is created this picture. Here's the pipe, and it constricts down to a smaller pipe. And a fluid's flowing through, and it has to get through the smaller part. Okay, that's basically what you've done by putting your thumb over the end of the hose. And so what we know from experience is that the water will shoot out further, which means by kinematics, if it shot out further, then it means it had to be moving faster. And so sure enough, that's what happens. When fluid is flowing through a pipe, if you constrict the pipe, the fluid will flow faster. If you expand the pipe and make it bigger, the fluid will slow down. And the reason is this. Let's say it didn't happen. So pretend we live in a universe where that doesn't happen. The fluid flows at the same velocity no matter what. Well, in this example, let's say we have a gallon of water flowing through this first big part of the pipe. So here's R1 and here's R2. So through the big part of the pipe, you have a gallon of water flowing per second. Then it gets to this constriction. There's a much smaller pipe, so not as much water can fit. And if the water didn't speed up, what would happen? Well, you have a whole bunch of water coming in, but only a little bit coming out. So you start to get a buildup of water here where the constriction occurs. And it just keeps building up and building up because the water can't get through. And it just builds up until the pipe explodes. Because there's just so much water built up, it has nowhere to go. It's like a bomb. Well, thankfully, that's not what happens in the real world. Rather, what happens is something called continuity. Continuity. And basically what continuity says is the flow rate of a fluid. So, 1 gallon of water flowing per second, or 15 gallons per second flow through this pipe. The flow rate in a pipe system is constant. So if you have a gallon of water flowing per second in one part of the pipe, then in some other part of the pipe, it should still be 1 gallon of water per second. the same flow rate, not the same amount of water or the same size of water or anything. It's the flow rate. Now, it could be the volume flow rate, which is like a gallon of water per second, or it could be the mass flow rate, which is like a kilogram of water per second. Usually we talk about the volume flow rate. A gallon of water will flow through this pipe per second. And it doesn't matter if we change the size of the pipe. If we make it bigger, we make it smaller, all sorts of stuff. No matter what, everywhere we check, the fluid will flow with the same flow rate, not the same velocity. So if this is true, then we say, okay, well, what's the flow rate? It's like the volume over time. That's the flow rate. A gallon of water per second, a cubic meter per second, whatever it is. That's called volume flow rate. And we say, okay, I want an equation which will tell me, depending on the size of my pipe, how will the speed change? Because if the flow rate is the same, but I make a smaller opening, so you would think less water can fit, then the water has to speed up to make in that same 1 second, you still get a gallon. So we think about the unit volume per time, and it turns out that the way we can create the equation is to say the area of the pipe at one location times the velocity of the fluid in that part of the pipe. Okay, now let's check the units of this. Area is meters squared. Velocity is meters per second. And so if we have area times velocity, we get meters cubed per second, which is meters cubed is a volume. And second, of course, is time, which right there is the volume flow rate. So the size of your pipe, the area, and when I say area, what I mean is the opening, the size of the opening in the pipe. So if we think about this pipe like a cylindrical pipe, then the opening is that circle that the water is flowing through. And so it's pi r squared. The area of the opening is pi r squared. So the area of my pipe times the velocity flowing through it is constant. That's the flow rate doesn't change. So A1 V1 is A2 V2. And that's how we could figure out how the velocity will change. Given how does the pipe size change? And so one way this is rewritten is pi r squared 1 V1 is pi r squared 2 V2. Okay, same thing, area times velocity. And you can see, now we know why the radius is important. Because if you make the radius go down, you constrict the pipe, the velocity must go up so that the same amount of water can flow in the same amount of time. And now we have our two big equations, continuity and Bernoulli's equation. Okay, turns out that's what we're going to be using for a lot of these problems, these two equations together. Bernoulli is the main one. That's going to be the one that'll allow us to actually answer questions. And then it'll turn out usually that we have to also use continuity to figure out one of the velocities. You know, maybe you have a pipe of a certain size, the velocity of the water flowing through there is 10 meters per second. The pipe constricts and then goes up to the second floor, and I want to know what's the pressure up there. Well, the first thing I'd have to do to enable to use Bernoulli is I have to figure out, well, what's going to be the velocity up there? I know the first velocity, but I don't know the second velocity, which I need in Bernoulli's equation. So in order to get it, I first do continuity. Continuity equation will let me figure out what V2 is. Now that I know V2, I can plug it into Bernoulli's equation. So these two equations are connected. And a lot of the times, whenever you have to use Bernoulli's equation to solve a problem, you're also going to be using continuity as well. So they always go together. All right, any questions about these two equations or anything we've discussed so far? All right, well, I'll go ahead and leave it here. Obviously, next class, we're going to be working a bunch of example problems to see how to actually do it in practice. But this is the theory. These are going to be the two equations we're going to be using. Bernoulli's equation and continuity together. And we're going to work on pipe systems. Pipe does this, it constricts or it expands, and it goes for 20 meters like that. And I want to know what's the difference in pressure between the beginning and the end. Stuff like this. Also, next time, I'll talk about why most people have heard the term Bernoulli before. And that usually comes into play when people discuss flight, how airplanes can fly. And it's actually Bernoulli's principle, which has allowed us to determine how to build airplane wings in a very specific way to allow for something as heavy as an airplane, which we know has a bigger density than air, to float, to fly. And it's a very interesting thing. And it relates to continuity in terms of, the importance of the velocity of a fluid and how the velocity of the fluid and the pressure of the fluid are related. So next time I'll talk about that, and then we'll do a bunch of examples so that we can, see how to actually work these equations. But for now, I just wanted to introduce the material so you know what the language is, you know what the variables are and things like this, and we'll be able to get to work next time. So are there any questions before we go? All right, well, if there are no questions, you're free to go. I hope you enjoy the rest of your day, and I will see you on Thursday.
Okay, actually, I do have one question.
Sure.
So for pressure, right? In chemistry, we learn like a bunch of different units for pressure, right? There's like ATM, there's pascals, there's kilopascals, there's torr. I know that and you wrote down ATMs and pascals. Are we just responsible for knowing those two, or do we need to know the other conversions?
No, we'll only need pascals.
Okay, pascals.
Atmosphere, I mentioned because later on when we talk about something in fluids, and we talk about something called gauge pressure versus absolute pressure, then the term atmospheric pressure is going to come up. So I just want to introduce it now. But for us, pretty much everything we do will be in pascals.
Okay, cool. Thank you.
Yep.